we're now trying to relate the electric field strength to the electric potential. Let's consider moving a charge Q in the direction of the electric field from point A to point B over a distance of delta x. The electric field strength at this point will be E. Work done to bring the charge from point A to point B will be the force multiplied by the displacement, and in this case the force is EQ, where E is the electric field strength while Q is the charge, and multiplied by delta x. So another way to calculate work done is to make use of the electric potential, and in this case we'll be taking the electric potential energy at B subtract by the electric potential at A. So this will be the expression for that. And more important of all is that, as earlier concluded, in the direction of the field lines, the electric potential decreases. So therefore, in the direction of the field lines, A will be V plus delta V in terms of the potential, while actually B will just be V. So in this case, so the potential at A will be V plus delta V, while the potential at B will just be V. Hence, if we substitute that, the potential at B will just be V, and potential at A is V plus delta X. And as explained earlier, in the direction of the field lines, the potential decreases. So because of that, once you do the subtraction, you will have a negative sign here. The work done ought to be equal to each other. So by equating them, we'll be able to derive that E is equal to minus dV dx. This is a formula that will be used quite extensively in our applications later. So for the formula for actually a parallel charge plate where the electric field strength is uniform, E will be equal to V over D. D is the distance between the separation, while V is actually the potential difference between the two charge plates. Finally, to wrap up the section, we're going to be saying a few words about the electric field lines and the equipotential lines. So electric field lines are lines that emanate from the positive charge, and all the lines are coming up. The density of the line depicts the electric field strength. So when the electric field strength here is high, you can see that the electric field lines are closer to each other as compared to the electric field lines here, where the lines are more dispersed and more spaced out. So hence, we can say that the inner field strength at the inner circle is higher than the electric field strength at the outer circle. Let's now take a look at the equipotential lines. Equipotential lines are lines that join up all the points which share the same potential. So in this case, given this as a positive sign, you can find all these circular dotted lines as being the equipotential lines. And if all these lines represent 1 volt, 2 volt, 3 volt, 4 volt, and 5 volt, we could also use our formula E equal to minus dV dx to give us an idea of the electric field strength. You can see certainly that the distance here, the delta x here is bigger, but the potential difference between them is still 1 volt. So the electric field line is expected to be lower. Conversely, between the 1 and 2 volts, the electric field, the potential difference is still the same, 1 volt. But however, because the distance here is very small, it will give rise to actually a higher electric field strength. We also want to highlight that field lines act perpendicularly to the equipotential line, as observed in this example. Let us take a look at another example. In this example that we have a parallel charge plates. So parallel charge plates, by and large, has a uniform electric field between the charge plates. And the electric field between the charge plates can be determined by E equal to V over D, and V is the potential difference between the two charge plates.